Hi everyone, I'm Bin from Tsinghua University. Today I'll introduce our work, Patronus, High Performance and Protective Remote Memory. This is a joint work with my colleague, Professor Youyou, Qing, Minhui, and Professor Jiwu. Nowadays, data centers suffer from low memory utilization reported by companies such as Google, Alibaba, and Snowflake. To address the low memory utilization issue, a new architecture called remote memory is proposed. In the architecture, CPU and memory are physically separated into two network-attached components, compute nodes and memory nodes. Compute nodes are equipped with a mass of CPU cores and small local DRAM. Memory nodes host large DRAM with several weak cores. Compute nodes and memory nodes are connected by RDMA, a high bandwidth and low latency network. RDMA provides one-sided verbs such as read, write, and cast. They can operate directly on remote memory without involving the remote-side CPUs. Since remote memory allows independent scaling of CPU and memory and allows flexible resource assembling, it largely improves memory utilization and gets popular. There are many efforts to make remote memory practical on multiple fronts, such as designing efficient remote indexes, proposing easy-to-use programming models, deploying popular applications, and more. However, there's still an obstacle to cross on the way to a practical remote system, which is not explored by previous work, the protection for remote memory. We first talk about why remote memory protection is necessary. We'll demonstrate with two concrete examples where applications observe anonymous when running on existing unprotected systems. First, if clients are bugged or malicious, they can fill an illegal address in the RDMA request. In this case, the out-of-bound write can introduce data corruption by overwriting somewhere it's not expected to touch. Luckily, the unregulated read can lead to privacy breaches by scanning the memory. Second, the memory management race can also make the concurrent RDMA access illegal. The figure shows an example where the client is reading the memory that is concurrently being freed by other clients. The client is likely to get garbage data in this case. So we found that remote memory protection is a less discussed but vitally important topic. It's necessary especially for the workloads with shared access patterns, such as remote hash table or remote B+3. But why didn't previous work provide protection? It's because achieving flexible protection with high performance is challenging. The CPUs on the memory nodes are weak, but existing protection mechanisms are all expensive. Existing protection mainly relies on two RDMA features, queue-paired and memory region. Specifically, queue-pairs the communication channel for RDMA, and memory region describes the piece of remote memory registered to the NIC. They work well in restricting which verbs are permitted and what addresses are allowed to access. However, both mechanisms are still ineligible because they are slow compared to the RDMA data path. Each queue-pair operation can take 100 microseconds, and memory region operation can take up to 1,000,000 seconds for a memory area of regular size. They are 15 to 500 times slower than the RDMA data path. Due to this unacceptable performance, existing systems rarely manage permission in their critical path. For example, FARM, a popular remote memory system, never modifies queue pairs and only uses 2 GB large memory regions, leaving protection out of their consideration. Moreover, it's also very challenging for a protective system to remain robust on the exception path. The first problem is orphaned permission. When a client fails, he may hold some exclusive permission. If the orphaned permission cannot be reclaimed rapidly, the progress of the whole system will be negatively impacted. The second problem is protection violation. When a client issues an illegal RDMA operation, the associated queue pair will run into an error state, disabling subsequent RDMA requests. Recovering the failed queue pair is a millisecond-scaled process, and thus the application's execution will be seriously interrupted. Here we summarize our goals. Considering that remote memory systems are performance critical, we expect fast permission management on par with data paths. Since client failures impact system progress, we expect to react fast to client failures. Since QPair failures interrupt application execution, we expect system to retain performance under QPair failures. In a word, our goal is to designing a protective remote system that's high performance and robust under all situations. Next, I'll introduce our system, Patronus. Then I'll introduce our experimental results and give a summary. Patronus is a protective remote memory system. Like previous systems, it provides direct data access interfaces for the compute nodes and memory management for the memory nodes. What's different is that Patronus involves permission management. In Patronus, clients have no initial permission. Instead, they need to acquire one before their data access. With Patronus, the client's workflow becomes a three-step procedure. First, the client needs to start permission. They could allocate or acquire, which will be translated into an RPC to the memory node, with permission as the response. Note that the permission here is fine-grained, typically covering only a small part of a data structure, such as a bucket in a hash table or a node in a B+ tree. Then, the client can perform data access several times with the permission. Patronus checks and rejects any illegal access, such as the one touching an out-of-bound address. Finally, clients call revoke to end the permission. As shown in the workflow, Patronus introduces the protection for memory access and, meanwhile, the overhead. Next, we'll talk about what opportunity and techniques we adopted to make the overhead reasonable. Memory window opens the opportunity of fast permission management. It's an advanced but widely supported RDMA feature for access permission. The memory windows are byte granularity and lightweight. As shown in the figure, they have a low latency on par with RDMA data path, which is 1 microsecond constantly. Memory windows have a favorable performance because, unlike memory region, they interact with the NIC asynchronously and purely in user space. The memory window offers 3 types of operations: byte, unbyte, and rebyte. Byte in a memory window exposes the access permission and return the permission token, while unbyting will invalidate it. Rebyte in a memory window is equivalent to an unbyte followed by a byte, but with less overhead. Although memory windows open the opportunity, the naive use of them are still not enough in many ways. In terms of performance, we wish our system to perform even better, considering that the CPUs are weak on the memory nodes. In terms of functionality, the window, which is deployed on the memory side, is unable to detect any client failures. Moreover, although the memory window protects against illegal access, it does not protect QPair from being corrupted. We still need software efforts to achieve all our goals. We first try to improve the common path performance. Our first technique follows the insight that the same protection semantics can be achieved with fewer memory window operations. Therefore, the memory node overhead can be further reduced. This is possible by leveraging the pattern of request in the system. First, we notice that every permission comes to an end. By noticing that byting and unbyting operations are likely to coexist, we can combine the byte and unbyte operation into one rebind, even if they are unrelated. In this procedure, the memory nodes scan and hand over the windows among the requests, as shown in the figure. As a result, the number of window operations are reduced to a half. Second, memory access exhibits spatial and temporal locality. With spatial locality, we can combine multiple byting operations into one if they are contiguous in the addresses. Considering temporal locality, we allow permission to be reused if client reaccess occurs. Patronus uses the lease to handle client failures. The memory window itself is not aware of any failures on the client side. To compensate, we introduce the lease semantics from the software to enable failure detection. We let the memory know to poll for expired permission periodically. By doing so, orphaned permission will be reclaimed automatically by the system. However, using this inevitably introduces the lease management overhead. Our idea is to offload the extension overhead to the client side, where a mass of powerful CPUs are equipped. This is possible by noticing a special property from memory windows. They are fine-grained enough to expose a single variable with reasonable overhead. With the help of window, we can expose the lease time variable to the client and allow clients to update the variable via one-sided operation, where memory nodes have no overhead at all. As a result, the extension only costs one inbound RDMA operation, which is cheap. Recall that illegal RDMA operation can turn the associated queue pair into an error state. To prevent application from being interrupted by queue pair failures, our third key idea is to over-provisioning queue pair resources to conceal the interruption. Specifically, each client will be assigned an initial queue pair. On queue pair failures, we transparently promote a healthy queue pair to substitute for the failed one. In this way, the client can resume its execution immediately on the new queue pair. Note that we only need to over-provision a small number of queue pairs because the failed queue pair can be recovered in the background and rejoin the queue pair pool when the recovery finished. A special property of memory windows enables this queue pair switches technique. Window can remain valid across queue pairs. With this property, the client does not have to reacquire a new permission on the new queue pair. As a result, downtime under queue pair failures is low. Next, I will report the experimental results. We use 4 machines as testbed and emulate 3 machines as compute nodes and 1 as memory node. The compute nodes does not cache remote data, and the memory nodes only use 4 CPU cores. We evaluate both the common path and exception path performance for Patronus. We conduct thorough evaluations to review the common path performance. We evaluated 4 state-of-the-art remote applications. They are one-sided data structures, including race hashing and concurrent queue, and famous function-as-a-service workloads, including image processing and data analysis workloads. For each application, we adopt Patronus to enable protection, where extra Patronus operations are introduced, denoted as the blue line in the figure. We compare Patronus against the vanilla unprotected implementation, denoted as the dotted line, and against other protection competitors. As shown in the figure, Patronus offered up to 5.2 times better throughput than all the competitors. The better performance comes from the use of memory windows and our careful software co-design. Furthermore, the overhead introduced by Patronus is no more than 28%. It's because from our empirical evidence, the overhead of one Patronus operation will be amortized into several RDMA operations, so the overhead is also amortized. To demonstrate the performance on the exception path, we conduct 2 experiments. The first experiment focuses on client failures. It emulates the case where clients are loading data into race hashing and a client crashes during resizing. Since the vanilla race hashing does not support cascading resizing, the client crashes while holding a lock, negatively impacting system progress. Patronus involves lease semantics, which detects and handles client failures, so the system can resume progress as a result. The second experiment focuses on queue pair failures. It emulates the case where an illegal RDMA operation corrupts the associated queue pair. Without our mechanism, the client has to wait for a full queue pair recovering procedure before continuing the execution. introducing the high interruption of 1 millisecond. Our over-provisioning mechanism successfully conceals the interruption to tens of microseconds, 8% of the baseline. So in this paper, we propose Patronus, a high-performance protective remote memory. It offers remote protection, which is a less discussed but important topic. It's very necessary to avoid anonymous for remote applications with shared access patterns, such as hash table and B+ trees. Patronus achieves high performance and robustness thanks to 3 techniques: memory window operation reduction, client collaborated lease, and queue-pair over-provisioning. We applied Patronus to 4 real-world applications and show by evaluation that Patronus has a low overhead and high performance. Please read our paper for more analysis and evaluation results. Thank you for listening. I'm open to any questions.